In this video, we will cover everything you need to know about data modeling, and this will be your one single place to master data modeling for data engineers. We will start with the basic. We will understand the core foundations of data modeling, from understanding different levels of data modeling, understanding difference between OLAP versus OLTP, modern data stack, overall data modeling process, how to actually build a data model, understanding ER diagrams, normalization, different normalization forms, understanding dimensional modeling, slowly changing dimension, one big table. And at the end of this video, we will do the hands-on practice where you will build Uber-like application data model that will track everything about the user. So this video is going to be fully value packed. I hope you like this video. Let's get started. All right, let's start with our data modeling masterclass. We are going to learn so many different things, and this video is going to be fully value packed. At the end of this video, you will master the core of data model. So we will understand the three layers of data modeling, such as conceptual, logical, and physical layer. We'll also talk about the different approaches of modeling, such as 3NF, Kimball, Data Vault, One Big Table, and NoSQL. After that, I'll give you the framework that you can use to design any schema in the world, right? Usually, when you go to the interview and they ask, like, you have to design a data model for that, people directly start drawing boxes and get confused like what to do next. But I'll give you the step-by-step framework on how do you actually execute on building a schema. Once we clear our core foundation, we will build the actual data model on the ride sharing application, or you can say Uber like application. So we will build a complete data model, and we will also talk about some of the anti-patterns you should avoid in interview and in the real production. So how to get most of this video, just watch this video into the proper sequence, because everything is into a proper story format. I'll take you on a journey of building a data model. So this will be a last video you watch on any data modeling. Once you complete this video, you will have a core understanding of how to build data model for any application. You will have a good idea to get started. You will also get the free design schema cheat sheet that is available in description. You can also practice more questions on data vidya. We'll talk about that as we move forward. And if you have any questions, feel free to comment. Okay, but by the end of this video, you will never freeze on design a schema question again. This is my guarantee, right? Once you watch this video from start to end, you will have complete understanding on how to build a data model. So that is a promise I'm making. So we'll start our video with our foundation. Now I have created the PPT. I also explain you visually things when I'm thinking out loud, and I also refer this notes, right, to explain you, because this is a visual notes that I've created on my data with the website. You can also open these notes and read it with me. I will explain you them one by one, so it will feel like a story that I'm telling, and it will be much more fun because I've added a lot of cool visuals here that will help you to understand things visually, and I also draw a few things for you so that you can understand. Okay, so you can go to this link. I've added this link into description. You can read it with me. If you don't want, you can just watch the video also and take notes on your notebook. Okay, so let's start with our foundation, right? What is data model? This is one of the most important thing you need to understand to get started. Now, again, when we are working in the real world, we know that, right? Our data is coming from many different places. So let's say I use iPhone. Inside the iPhone, I have the Instagram. Now, when I use Instagram, I do a lot of different actions. So first of all, I open the app. Okay, I comment on something, I scroll the reels, I like something, I share it with people. Now all of these actions that you're doing are actually get stored into a database. It can be stored on any storage location, but let's take the example that it is getting stored inside a database like RDBMS system of Postgres, MySQL. Okay, now when you store this database, right, either you can directly store as it is, like just dump the database with no format, no structure, just like that you store it. But the problem with that is that if you want to find any information, you will not have a clarity, right? Let's say if I want to find information about the user comments or likes, I will have to like spend a lot of time thinking and figuring out what this data is all about, and then I extract the information, maybe using some script or query. Data modeling is the approach of converting all of this scattered data, raw data, into a structure format. Okay, so that whenever you need to find the right data, you can easily find using this structure. So that is the core. Okay, so raw data, as you can see, it is like scattered across multiple files, formats, and different things. When you model this raw data, which basically means you are creating a data model, you define a structure, you define a relationship, and you ensure the consistency across the system. Okay, this is the start of data model. The core idea is you will have a lot of data available. You just need to store it into the proper structure. So it is a process of deciding what to store. Okay, what do I want to store, how to structure it, and how tables relate to each other. So at the core, data modeling is a visual representation of how your data is actually getting stored inside the database. One way is you can store as it is, it doesn't matter, okay, but the best way is to actually create a structure out of it. So it is a blueprint for your database. So think of this way, right? If data engineering is building a house, then pipelines are basically plumbing and wires. SQL is a construction language. Data modeling is the architecture, right? So if you put the kitchen on, let's say, terrace, it doesn't make any sense, right? You need to define a house properly. You need to make sure the stairs are proper, the kitchen is at right place, the sink is at the right place, so it goes to the drain. All of these things define the structure of the house. The same way, data modeling defines the structure of your database, right? The way you store your data actually gives you the right output at the end. This is the best practice that you start when you design an application, and it goes to the journey of analytics, right? So if you have stored data into like a messy format, into like 1,000 different tables that has no relationship, no consistency, just like that you store it. Now when you want to analyze this data, when you want to build a ETL pipeline or data pipeline, you will have very hard time building it, because you will not understand what this data is all about. But if you have a proper structure and documentation about it, it will be very easy, because you will know, okay, this is the key, this is the table that I want to join with this key, and this is the output that I get. So this is the core idea of data model, that you define a structure, you convert the raw data or messy data into the proper structure format, so that it has a structure like this, it has a relationship and the consistency across the universe. So right, whenever the new data comes, it follows that format. Okay, now at its core, data modeling answers three questions. Okay, what entity exists in your business? First of all, again, all we are doing these activities for the business, right? Business can be anything. For example, we have e-commerce business where we help people buy products online and it gets delivered. We have, let's say, Uber like application where you can book a ride. We have Instagram. All of these at the core are business, right? They are giving something. E-commerce, you can buy products. Uber, you can like book a ride. Instagram is for entertainment, Netflix for entertainment. Like all of these are the different businesses available. Now at its core, we have to define the entities in the databases, right, for your business. For example, in the case of e-commerce, we have customers, right? Customers are there. We have orders, customers are ordering something. We have products, customer orders product. We have shipments, we have payments. So these are the things we need to track, right? These are the data that are coming. So we need to think from that way, from the business way, that okay, if this is an e-commerce business, what are the things that we can track? Okay, this is what we call as the entities inside your business. After the entities, we have to describe the attributes to those entities. For example, a customer has name, email, city, it can have a sign up date. Same with the orders, like order has order amount, order date, status. So what information matters to us? What are the information that we want to collect? Okay, so that we can have a proper structured data model. And how do these entity relate to each other? Okay, three things: entities, attributes, and the relation between each other. Basically, customer can place many orders. An order can contain many different products. A product belongs to one category. How do these things connect? The answer to all of these three questions, like entity, attributes, and relation, is basically your tables, columns, and the keys, like primary key and the foreign key that we create. Okay, so if you get this right, the life will be much more easier for data engineers when you move forward. If you mess this at the start only, then it will be very difficult for you to actually get the right data and analyze your customer. Okay, so this is the core of data model. So now that we understand what data model is basically converting our messy data into the structure format and storing it into a database. So let's talk about why data modeling matters, okay, with numbers. Now the impact of data modeling that you can see, right? You have a bad data model and this is a good data model. If you have a bad data model, okay, it will cause a chaos around the entire business. You will have siloed data. Basically means data is stored across like 100 of different tables. You will have redundant data. Again and again you will store same data into different tables. Inconsistent definition. So let's say order number might mean something else in one table and something else in another table. Hard to maintain, complex process, slower performance. So this will result in high operational cost and a poor user experience. But if you have a good data model, okay, it is properly well designed entities, so all of the entities make sense to your businesses. It is normalized data, consistent definition across all of the system, simple and clear processes, fast performance, scalable, easy to maintain. So everything is good here, everything is bad here, basically, right? If you don't perform a data model, it will be very difficult for you to actually manage your entire business, because you will not be storing the right data in your database. So these are the core metrics. Like, you have a query performance, it has like huge impact. So let's say if you are designing a dimensional model, and if you have created a proper structure, like a star schema, we'll understand about that. And if it is just a one fact table and one dimension table, you can join and get the query, it will take like 10 to 20 seconds. But if your data is stored across hundred of different tables, and to get one output, such as what was the revenue of last year for this particular product, okay, if you want to get the answer for this, and if you have used like OLTP, but so if you want to get answer for this, and if your data are stored across like 10 different tables, you'll have to do a large join to get one output. So this will take even 5 to 10 minutes, even more than that. Okay, so this matters. Second is the development speed. Also, when the model is clean, building new dashboard is piece of a cake, right? You can just get the right data and you can actually start building it. But if the model is messy, it doesn't have the clear table names, mixed granularity, no documentation, so every report that you want to create, you will go in a journey of figuring out what data to use and actually get it. But then also there is a data trust also. So in a company, right, there are a lot of departments. For example, Amazon, right, there are shipping department, order department, user department, refund department. There are many departments, right? And these departments use data from each other, right? So shipping department might want to get the information about the orders, or refund department might want to get the information about the order and shipping. So they collect data from different business units to build the analytics, so that they can track the entire business. Now, in this case, the business team will not have a trust on this data. They will always question that, does this data make sense, right? We are seeing that in real life, the order is around 100, but this graph is showing that we have like 500 plus orders or 500 plus refunds. So if you don't properly define a data model, you will not have a right data, and the data trust will go down for that particular use case. Okay, so a well-modeled warehouse produces a number that matches the actual reports. Okay, revenues in finance dashboard equal to the revenue in the executive dashboard equals to the revenue in the product dashboard. So every data matches across the organization. But in a poorly modeled warehouse, it will produce three different numbers. One will show something else, one will show something else, third will show something else, right? So this will create a distrust in an organization that these data are not right. And also the maintenance cost, right? If you don't design your model properly, you will have like to spend a lot of time making sure everything is right. But if you define a structure from the start only, it will be much more easier to define. Okay, now that we understand what is data model and why do we need data model in the first place, let's start talking about the actual data modeling, which is the three layers of data modeling. And three layers are conceptual level, logical layer, and the physical layer. Okay, we'll understand them one by one. This is the core concept of data model, so make sure you spend attention here, because if you understand this, then it will be much more easier to understand the uh, uh, further chapters. Now, data modeling happens at the three level abstraction. Understanding this level helps you to communicate with a different stakeholder. From business leader to the database administrator, using the right level of detail, right? These three levels are designed for different type of user, right? In organization, you have different users also, right? One is business people. They only talk about in the business term. They only look in the real world, like how the shipment is going, how the trucks are moving, what is happening onto the refund department, what is happening with the product team, what is happening with the order team. So they only talk about business. They don't care about the technological side. They only think, okay, in the numbers. They just want to see the final output and how the business is doing. Then there is a logical layer and a physical layer. So let's start by understanding one by one. The first is a conceptual model, or we can say a business view. The conceptual model answers, what are the important things in our business and how do they relate? This is the simplest question that you want to ask, whatever the business is, right? For example, at the highest level, you don't talk about like columns, data types, technical details, just entities and relationship. Something like this, okay? So if you're talking about e-commerce, we'll define a simple model, okay, with the entity and the relationship. For example, we have customers, okay, then we have orders, then we have the product, and then we have the shipment. Okay, so these are the four entities I want to start with. Now, customer places an order. Okay, order contains a product, order is shipped via shipment. Okay, this is the simplest, highest level view or conceptual level view that talk about what are the important things in our business and how do they relate to each other. This is not the place you talk about the columns, data types, and all of the other things. This is a place you just define the entity, which is a basically different units of business that you want to track and the relationship between them. So customer can place an order, order contains a product, order can ship via shipment. Okay, simple, very basic level. You can create a conceptual model in first 5 minutes of data modeling interview and show you understand the business domain before diving into the technical design. This is you should always do that. Let's say you go in an interview and they ask you, okay, design a data model for e-commerce application. What usually everyone starts doing is that they'll draw a table, then they'll do the orders and then order ID, order name, date, all of these things they'll start adding. This is not the right approach. First, you should just define entities and relationship. You just draw boxes and write customer, orders, product, shipment, and just define a relationship and talk to interviewer. Okay, this is the higher level entities that I've designed. Okay, if this makes sense, now let's move to the next step. That is a logical model. Okay, this is where you define a structure. So logical model answer what specific attribute does each entity have and what are the keys and relationship. Okay, this is a logical structure. So this is where you define the columns, primary key, foreign key, and the data types. But again, just onto the on paper, you haven't actually started writing a query or you don't create any table into the database yet. This is just a logical model for the documentation or for the still business people to get more detailed view of your data model. So this is high level. This is a little bit lower level where you provide more details. So again, same data model, but more things added. For example, inside the customer, we have customer ID, customer name, email, city, and sign up. Okay, and customer ID is our primary key. If you don't know what primary key is, it's basically the unique key you define in each table that auto increments so that you can find a specific information about a customer. So just like you might have your own customer ID on Amazon, or you might have your own ID in your Netflix, Instagram, right? You can think about, let's say, uh, Instagram username also. You can think of it as a primary key. They might be using some numerical value in the backend, but this is the simplest explanation that any unique value that can help you to identify one single row, okay, that is called as a primary key. It can be auto incremented or it can be created with the unique approach. So this is the primary key. Then the same goes with the order. Okay, so inside the order we have order ID, that is the primary key of the table. Then we have the foreign key. Foreign key is basically you reference the primary key of the other table. For example, there is a customer ID and then you use the customer ID inside the order ID. So you know that whenever any order comes, right, let's say I order iPhone from Amazon, the new order ID will be generated for that. And it will store the information about the customer ID, order date, total amount, and status. Okay, then we have the product ID. Product contains like ID, product name, category, price, and brand. And then we have the shipment. Okay, shipments are basically shipment ID, for which order the shipment is happening, shipment date, status, and tracking number. This is the core. You can let me just give you the more understanding about this. Let's just spend some time here to understand this. For example, let's say we have a customer here. Okay, customer ID as 101 is my customer ID. Now the customer name here is Darshil. Okay, email is my Darshil at, let's say, gmail.com. City is, let's say, Mumbai, and sign up date is, let's say, today only, like 30. Sign up date is my, let's say, 10 March 2024. Okay, now inside the order, this is my what is it? This is my customer table, and now this is my order table. So inside the order, the information will be stored like order ID. It can be like long string, like 100, like there are a lot of order ID. So just keep it simple. This is my first order in the application. So order ID is 1, customer ID is this 101 because Darshil ordered this particular product, and the order date is, let's say, again 11/04/2025, something like this. Total amount in that order can be like 4,500. Status can be uh, shipped, or let's say order received, or something like that, order received. Okay, so this is how the data will store. Again, inside the order table also you can store the information about the product ID. So you can also say that okay, this in this order, this particular customer ordered product ID as 02, okay, or 2. And in the product table also you will have something like this. So product will have some ID. Let's say product ID is 1, and uh, product name is, let's say, iPhone. Okay, let's just give this product ID 2. So we can say that inside the order ID 1 is ordered by like 101, that is connected here, which is Darshil. Okay, ordered iPhone on 11/4, 11 April, for amount this, and the status currently is order received. After that, you can track this order onto the shipment table and make update the status with the tracking number and all of the other things. So this is the core, right? Right now you are not designing this table and everything. You are just defining a structure that all of these data makes sense at the initial stage. So this is the logical model, right? This is where most of the data modeling interview happens, where you will spend majority of time implementing this column, which column exists, what are the keys, how does the relationship define, and also this like one to many and many to many relationship we'll talk about when we go into the ER diagram. But this is a logical model, and then the actual implementation. This is where you start writing the query onto the database, which is a physical model. The physical model answers how is this actually implemented to a specific database. So you start thinking programmatically, you start thinking in the SQL terms, like partitioning strategies, indexing, clustering keys, data specific to a platform databases, data type specific to your platform, storage format. So all of these things you start thinking about it, right? So you define the logical tables, then you can do the indexing, you can store it on the disk, you can define a partition. This is where you start writing a SQL query. Again, we go into the detail of SQL queries in our SQL video. So this is just an overview I wanted to give for this, but we'll mainly spend about this part of this. In most of our project we have done this also, the implementation side of it. If you have watched those videos, you might already know. If you haven't, you can watch it after this video, it will make more sense. I will give you the links of those video at the end of the video also, so how you want to take it forward. But this is the physical model where you actually start writing the SQL query. Okay, in interviews you will be occasionally touched on writing a SQL queries, like okay, that you have defined this, now define the physical model for this also, or just write a query to do this. So these are the 3 layers of data modeling. Conceptual, it is what are the important things of our business and how do they relate. You define something like this. Then the logical review, what specific attributes does the entity have, such as keys and relationship, like this. Then the physical, where you write actual query to store the data, optimized by the indexing, partitioning, and all of the other things. So this is the 3 levels of data modeling. Okay, always start with the first one, then you go to the second one, then you go to the third one. Do not directly start with this. Okay, now we will understand about this data modeling for OLAP versus OLTP, and this is very important for you to understand, because when you go to the interview, right, in data engineering you are mainly working on the OLAP side. You take data from OLTP and you push it to the OLAP. We'll understand what these terms are. If you already know, that's good, but if you don't, I'll explain you that in a bit. But understand this, right? If you want to build OLAP, you need to understand OLTP also, because if you don't understand this entire system, right, if you don't have any idea about this system, then you won't be able to build the OLAP from that. Okay, so that is the reason we will be learning this data model side, and in the future videos we'll understand about the dimension modeling. You can comment down below if you want the video after watching this video. If you like this video, okay, and if you want the next part of this video, then you can tell me, I'll create that. But in this video I want to mainly clear your data modeling fundamentals, and then we'll move to the dimension model, and I'll explain you both right now. Okay, so OLTP and OLAP, the full form is basically online transactional processing and online analytical processing. Over here we will have OLAP. Okay, so these are the two system or data system we have, and both have a different use case. For example, the way you model data for transactional system is fundamentally different from the analytical system. So inside the online transactional processing, you are mainly designing your database for the application. For example, the application that powers your website, mobile app, or API. They handle the individual transaction, such as A customer can place an order, a user updates their profile, a payment is processed. So OLTP models, right, are used mainly for faster writes when you want to start, when you do a faster insert and updating. Data integrity, so you have no duplicates, no inconsistency, no orphan records, and normalization. Data is split across many different tables to reduce the redundancy, right? You don't store the product name across multiple tables. Okay, you just create a one symbol table for products, and that is it. And whenever you need it, you use it the reference ID or the primary key, foreign key, to get the information from that table. So you can see this is stored across more and more tables. This is the normalization form. We will understand about the normalization, but the core idea is that instead of storing information across the same table again and again, duplicate information, you create a specific table for that particular information and store it in a separate table. So you try to divide your data into many tables. This is usually happens in OLTP. Okay, you have like hundreds of different tables that are storing information, and OLTP is mainly used around the application side. So let's say I use Instagram, I use Amazon. I'm not connected to the OLAP database. I'm connected to the OLTP database. OLTP databases are like PostgreSQL, MySQL, Oracle database, Amazon Arera, RDS. It is available. Okay, so let's take the example of PostgreSQL. Okay, so that is an OLTP database. The core idea here is like this. Okay, let me explain you. OLTP, online transactional processing, and then I have OLAP, online analytical processing. Let me change the color of this also. Okay, now this is mainly used around website, apps, APIs. This is used on the analytics side. So when I want to answer question such as what was the last 3 years of revenue for this particular product, if I use the OLTP type database, which is basically PostgreSQL or MySQL, I will have to join let's say 10 plus tables to get the answer. Okay, because I will store data into normalized form. But inside this OLAP that is built for analytics, and the databases are basically this BigQuery, Snowflake, Redshift. Okay, these are the databases specially built for analytics. That basically means you can get the same answer by scanning two tables and get result in 1 second. Here it might take 10 to 30 seconds to get the same output. Again, depends on the data size. So if you're working with a large chunk of data, it will take more and more time, even 5 minutes, 10 minutes, half an hour. But this is designed for analytics. This is designed for transaction. This is a core concept that you have to understand. OLTP, online transactional processing. Okay, this is great for when you want to do faster read writes, when you want to make sure data has no duplicate, no inconsistency, and data is split across the multiple tables. So this is a very great for application, but it is very terrible for analytics because you will have to join 10 plus tables. But online analytical processing, these are the systems specially created for analysis only, and they use something like this star schema and the Snowflake schema. This is the example of the star schema, where you have the fact table in middle, okay, and you have the dimension tables across it that stores the information about the attributes. For example, fact tables will store the information about the keys and the quantity, unit price, the measurable values, and dimension tables will store the information about the information that relates to those things. For example, dim product will have the information about the product name, brand, category, all of the other things. Again, this we will go in detail in our future videos, the part 2 of the video. In this video, as I said, we will talk about how to design this. In the part 2 of this video, we will talk about in detail about how to design this. But let me just give you the overview of that. And if you want to again go by your learning, we have the notes available for that as a dimension modeling, fact tables, keys, slowly changing dimension. You can also check them here, but let me just give you the overview. So it works on the fact and dimension tables. Okay, OLAP systems are your data warehouses such as Snowflake, BigQuery, Redshift. They handle the analytics queries such as total revenue by category by month, total revenue by category by month, customer lifetime value by region, year over year growth by product line. Okay, so OLAP models are usually used for faster reads. So if you want to query millions of data across table within seconds. You can do that. Query simplicity, analysts can write straightforward SQL query without navigating to 10 plus tables to join. And denormalization, right? Data is intentionally duplicated to reduce the join and complexity. So here we do the normalization. Okay, we'll talk about the normalization. Basically, we divide our data as many as table. We divide our data into across multiple tables it is possible, and then we use the OLAP, which is the analytical processing, where we try to create a minimum tables and try to store data in few tables so that we can quickly get, let's say if I want to get the information about the product, I can just do the product key, join here and get all of the information. Rather than here, if I want to get, let's say, the information about shipment for that particular order and a customer, I will have to join customer table with the order table, also with the product table, then the shipment table and the shipment item and the payments table to get the final value of the revenue or something. Okay, so I'll have to join multiple tables here, and this is not designed for that. This is designed for storing data without a duplication. This is designed for analytics only. Okay, so let's just summarize this. OLTP transaction, online analytical processing. Okay, purpose, this runs the business, basically process the transaction. Whenever you make a transaction in a banking application, whenever you order something, this is one single transaction. This is used for analyzing the business. Okay, users are applications and APIs. The users here are analysts, data scientists, data engineers, dashboard, BI expert. Query pattern, a single row lookup and updates. This is a full scan and aggregation, optimization, write speed and consistency, read speed. Modeling approach, we use the normalized 3NF here, and we use the denormalized such as star, schema and one big table. Typical size gigabyte to low terabytes, and this is a terabyte to petabyte. Examples such as Postgres, MySQL, Snowflake, BigQuery, Redshift. Okay, so this is the difference between OLAP and OLTP. Okay, so we understood few things: what data modeling is, why it matters, three levels of data modeling, and difference between OLTP and OLAP. In this video, we'll mainly focus on OLTP side only. Okay, OLAP will focus on next video. Now this is clear. Let's look at the data modeling in the modern data stack. Okay, this approach of data modeling that we are doing right now made sense 10 to 15 years back when we were using our databases that were very limited in computation and the storage, right? We had like very limitation power, so that we had to make sure when we store our data onto these databases, they are efficiently storing all of this data, because we have the limitations on processing and the storage. So we make sure every data that we store is properly stored into proper structure only, so that we don't waste all of these resources. But now storage with the modern data stack is nearly free, right? If you go on a Snowflake, monthly storage cost might be around $20 to $30. That is not that big. So even if you store the data into the denormalized form, like even if you have duplicate data not storing into the proper structure, that is not the main concern, right? You might lose some time onto the query thing, but it won't have that much impact on the initial stage. So now the way you architect your data model into the model system has changed a little bit. Okay, so storage is nearly free. Compute also scales independently. So in BigQuery, you pay based on the query that you scan your data. For example, you pay per query based on the byte that is scanned. In Snowflake, you can spin up the large data warehouse and quickly, run a large query in few seconds, and you'll get the result. Earlier, it was mainly about fitting within the hardware, right? So data modeling decision that we used to take, we was to make sure that, okay, we have the limited power, so we want to make sure everything is getting stored. But now it is more about making queries efficient and easy to write. So we don't think about now storage and computation, because it is very cheap and freely available. So we mainly work around making the query efficient and easy to write. And also columnar storage changes everything, right? This OLTP databases that we used to store data into a row format. So when you store a data, let's say customer ID, customer name, email, city, and sign up, this will create a sort of row like this, okay, in the row based. Okay, and inside database it will store information such as like 101 comma Darshil comma, let's say this information here comma, something like this, Mumbai, and last is date. Okay, so in this case, if, okay, like this, they will have, it will store all of this data into the row format. Why it is not getting selected? Wait, yeah. Okay, it will have something like this, okay, like this. It will store all of this data into the different rows. So this is what we call as a row level storage. But if you have a column level storage, instead of storing all of this information into the raw format, it will have a single column that will store information about, let's say, 101, 102, 103, all of the IDs dot till the end, last one. Okay, the same it will go for the individual column. So if you have let's say a column, let's say this is order table, and it is storing the information about the total amount. Okay, inside of one single column, it will have total amount available here. Now this total amount, it will store like this. Okay, 4,000, 4,000, 2,000 for different users, something like this. Okay, so if we are getting we are storing all of the information inside of a row base, if we want to get the sum of all of the total amount for that particular customer ID, let's say, okay, what we'll have to do, we will have to scan all of these row individually one by one. So database will scan all of these individually, and then it will pick one single column. So here we, let's say we also have amount here, 3,000. For this we have let's say 2,000, and for this we have, let's say, 5,000. Okay, so what you will do, it will scan each and every row, and then after scanning the row, it will pick this single column at the end and then do the sum and then return the output. But if we are using a columnar based format, okay, instead of scanning all of these single row, let's say if you have millions of row, it will have to do millions of scan and then pick the single column. It will directly go to this column, directly do the sum and give the result. So this will take, let's say, 1 minute. This will take maybe 1 second. Okay, that is a modern columnar storage changes everything, right? Modern cloud data warehouse are stored inside the columns, not row. So this means that 200 column table where you only query the 5 column out of these 200 columns is same as just querying the 5 columns from a table, right? So if it is stored inside the columnar format, you just have to pick the 5 column and it will be able to give you the result faster. Then the schema enforcement is also optional in modern data stack, right? Snowflake BigQuery supports like various type of schema such as variant, JSON. So you don't have to store your data inside the database into a proper structure format like, you know, integer, float, double, and all of the other things. You can directly store data as it is and it will give you the result. So this is how the data modeling happens in modern data stack, where you don't worry about just structure now. You only worry about making sure your queries are fast, it is simpler, data is available quickly. All of these things you focus on, but the fundamentals haven't changed. Okay, you still need to understand the grain, right? The grain is basically if your data is on order ID level, or it is on the product ID level, or it is on the customer ID level. What is the grain of your data? Like, what is the minimum what do you say, what is the lowest level of aggregation? Can you aggregate data on the product ID level, customer level, order ID level, shipment level, whatever it is, right? You need to understand the grain of data. You still need to separate the fact and dimension table. You still need to think about slowly changing dimension, confirm definition. Cloud warehouses change the cost structure and modeling decision, not the logic behind them. Okay, so it is still the same, right? You still have to model it properly. So if your data is growing everyday basis, and if you don't have a proper structure behind that also, so your cost will also increase, storage will also increase, and you will have a lot of redundant data, messy data available, and it will also result in the same issues that we had, right? So instead of paying like $20, now you will be paying $60. So why do you want to waste like $40 on top of that? So this is what the data modeling is. In the modern data stack, people are mainly focused on, you know, getting the output right and faster, not thinking about the storage and the cost anymore. But this is the best practice that you can always have to save cost into the organization. So this is how you do a data modeling in modern stack. Where is the structure is not the case anymore, but you still need to have a core foundation. So now let's understand the data modeling process. So when you go to an interview and they tell you, okay, now design a data model schema for e-commerce application, how to go about it? I'll give you the 6-step framework that you can use it to design any data model in any interview. Okay, First and the most important thing here is understand the business process. If you understand the business process, you can draw any schema. So before you draw a single table, understand what business are you modeling. Are you modeling sales, inventory, user engagement, customer support? What is the goal of business here, right? Again, taking example of Amazon. The Amazon might want to track the orders information. They might want to understand the shipment information, the sale information. Okay, what is the final outcome? I keep saying this, right? The goal of every data project is to provide a value to a business. Okay, a value can be provided in multiple ways: understanding customer, increasing revenue, finding a ways to fix the issue or bottleneck. For example, in shipment, there might be some issue going on that a truck is taking uh, 20 minutes to go from A to B warehouse, but it should ideally take 10 minutes only. Driver might be doing something else. So you can analyze all of these small things and improve the business. Okay. So each business process has its own event, measurement, and context. Sale Sales involves such as order, payments, customer. Inventory involves such as stock level, warehouses, products. So don't try to model everything at once. Start with one process. Okay, you define a one process. Okay, let's start with the sales. Now sales, we talk about orders, payments, customers. Okay, once that is done, then you'll think about, okay, inventory. Okay, order, customers will order products. So we need to make the inventory about the different things such as stock levels, warehouses, where it is located, products. So like this, you define the individual units of business. So we have, let's say, sales, okay, such as orders, payments, customers. Okay, this is related. Then inventory, we have warehouses, stocks. We can also have shipment. Here we will have trucks. So like this, you can have different units of business and the different functions that are going over there. So once you understand the business process, second step here is identify the entities. What are the things are in the business process? For example, customer, products, orders, stores, date, promotion. These becomes your table, right? Over here, like this orders, payments, customer, you think about what are the information that we can store about these different business processes, and you create a table around it. After this, you define the grain, and this is the most critical step, right? The grain declares what a single row in your table represent. For example, one row per order line, one row per daily inventory snapshot per product. Okay, so when you store information about orders, okay, it will store on the order level. So order ID will be 1 2 3 4 5, whatever it is, right? So the grain of order table is based on the order ID level only. Same go with the payment. Okay, payment will be based on the payment ID. So payment ID will be the grain of payment. Okay, same goes with the, let's say, warehouse will have a grain of warehouse ID. Usually you use it as an ID also. It can be a combination of multiple ID. Okay, so like this, you define a grain for each and every table that you create. After that, you define the attributes and relationship that we already understand. What are the columns does each attribute have? For example, entity have, such as order has order ID, name, date, status, all of the other things. Then you choose your modeling approach. Okay, do you want to use star schema, snowflake schema, data vault, OBT? Depending on the application that you're building. For example, you're building a data model for, let's say, e-commerce application for storing data, then you go with the 3NF. Okay, if you are using building for analytical databases, then you have to talk about, do I want to use star schema, snowflake schema, one big table, all of the other things you can use. And then you do the simple query validation where you can join the different tables and get your final result. Now, this is a common approach, right? This is not just for the data model. This is the entire process of building a data model. You define the business process, you define the entities, you define the grain, attributes and relationship, choose your modeling approach, and then you validate against the query. Now let's talk about some of the common mistakes that you usually make in an interview. Okay, so one of the most common mistake, right? Copying OLTP schema into your warehouse. This is most of the people do that. Again, OLTP uses normalized version of tables. Okay, and if you directly use that schema onto the Snowflake database, then it will not give you the efficient output. So this is one mistake. Second is skipping the grain also. Like if you don't properly define like one row is equal to one order ID, then or whatever it is, like one row is equal to one payment information, then it will be very difficult for you to create a relationship between them. ignoring historical changes, over engineering for future, like you define more and more complex stuff, and also not using proper naming conventions. So common mistake you do is that you don't talk about the business context. People, what they start doing is that, okay, I have to build a e-commerce data model. I'll directly start creating a table, different boxes, join this, and start doing that. But first define the business context. If you don't define that, people usually focus on the logical layer. They ignore the conceptual layer, they ignore the physical layer. So the right approach should be to focus on the conceptual first, then logical, and if they ask you to design a physical, you can also do that. So continuing with the common mistake in data engineering interview, the wrong thinking is I only design a table. So if you don't have a business understanding, if you have a missing relationship, poor performance, scalability, it is incomplete. Okay, right thinking is what are the important thing for the business, conceptual, then logical, and then the physical. So when you're inside an interview, it is not just they ask you to do something and you're doing it. It is a discussion, right? You talk it out loud. Okay, this is the e-commerce application. I think we can start with the conceptual model, and this is how I want to start. I'll define the orders, I'll define the customers, product, and shipment. Let's start with this. Okay, let's create a conceptual model around this. Order depends on shipment. A customer purchases the product, a product is getting shipped by this particular shipment company or whatever it is, right? You define this entire thing. Then if you can think more of the different things such as payment information, the inventory information, you try to add it. Once you ask the interview, okay, let's start with this one. Okay, then you go with the second approach, which is a drawing the logical model, where you start defining the attributes, relationship, and all of the other things. If it looks good, you try to add more and more things, and then you finalize. Interviews always evaluate the four things. First, can you ask the right question? So before drawing anything, you should clarify what business process are we modeling, what are the end user, what questions do they need to answer, what's the data volume. Then do you understand the grain, can you reason the trade-off, can you handle the follow-up, right? They keep asking you different things. Okay, what if this things happens and what will you do? So again, if you want, you can read this entire thing I have created for the interviews also only. Okay, so if you want to deep dive, I'll suggest you to read this entire blog. But now that we understand what is data modeling, let's now understand the modeling side of it, right? Entity relationship diagram. This is like a lower level version of the creating data model. Let me just have water. So now that we understood the data model, let's talk about modeling. Okay, entity relationship diagram and how to read and draw them. This is little bit on the academic side. If you have taken like engineering course in college, CS or IT or computer science, whatever it is, you might have this in your database chapter. If you haven't, totally fine, but this is usually used in an academics level. This is like the first step to creating a data model. Okay, and then you go one by one to creating a production level application. Okay, so before you design a single table, you need a way to think visually about data. And diagrams are the whiteboard language of data modeling. In interview, they always expect you to draw all of these boxes to make sure you understand what you're building. So let's start with the what is diagram. Okay, again, it is similar to data model only, and it is a sort of data model only, but this is a academic notation. We have a Shen notation and Crowfoot notation. We'll understand that. Okay, so business requirements are messy. Order have items, orders have place date, each item has the price quantity, we need to calculate order tables, products have this, many details, product belongs to category. All of these things a business we have. Diagram is a clear and structured way. Just like a data model, diagram, you define different entities and attributes to that particular entity. For example, one customer places n orders. Okay, we'll understand this 1 to n thing. Okay, then again, order have order ID, order date, status, total amount. Same goes with the order has order items such as quantity, unit price. This includes products such as product ID, product name, description, price, belongs to category. Okay, like this, you define rectangle that is called as an entity, and these are the attributes. So diagram is a visual representation of three things. One is entities, attributes, and relationship. Entities are the things you store such as customers, order, product that we already know. Attributes are the properties such as customer name, order date, price. Relationship, how those things collect. A customer can place an order contains a product. All of these things you define. Again, think of it as a blueprint. Now you might have a question like, what is the difference between data model and model? It's just a two different way of drawing it. That's it. Okay, we call it as a Shen notation and the crow's foot notation. The Shell notation usually used in academics and traditional system. We used to use something like this. Crow's foot notation is an industry standard. Okay, so both are doing the same thing. One is doing the rectangle and using this oval format to define this in academics. Second is using this the data model format that we call, or the crow's foot notation that we call, is boxes inside a customer you define like a table only. Okay, so both are fundamentally same, just the drawing is different. Okay, so do not get confused like, oh, I learned about ER modeling and the data model. Both are same, don't worry about it. Okay, Shell notation is an academic standard. Entities are rectangle, attributes are ovals, and connected by lines. Relationships are diamond. You will see in the database textbooks and the university courses. When you go, you will always see that inside the academic. So as you can see here, this is my entity. This is my attributes. Okay, when I want to define a relationship, I use the this rhombus type, this diamond. Okay, to define that. And then we have a crow's foot notation. This is like industry standard. Entities are rectangle with attributes inside listed. Relationships are lines with the special symbol at the end indicate the cardinality. Like how many cardinality are basically how do they relate to each other. We'll get to that now. So when you are in the interview, you should always use the crow's foot notation. Okay, this is used in academics, so always go with this. Now, entities, attributes, and primary key. Okay, so let's say we have a customer table. The primary key is customer ID. The attributes are the name, city, email. The foreign key is the ID from other table, from the country table, which is a primary key of the country ID. So this is how you define, right? This is what we have already done. So entities is anything your business needs to track. For example, in e-commerce company, customers, order, product, shipment. In ride-sharing platform that we will build, we have the riders, drivers, trips, payments. Each entity becomes a table in your eventual database, right? So this is like a business that you want to track. Attributes, again, the customer name, city that we already understand, and the every entity needs a primary key that we already know, the unique identifier that distinguishes one instance from another. Customer ID for customer, order ID for orders, product ID for products. Without primary key, you can't uniquely identify a row or your relationship will fall apart. Again, primary key is very important. If you don't have a primary key, then you won't be able to understand the difference between different customer. Like Darshil, with my name, there can be 10 customer, right? Even with the same name and the surname, right? Darshil Parmar can have like 10 different records. Now you can argue that, okay, I can use email as a unique identifier. Okay, I can keep the email as the primary key because emails are always unique. But what if a user updates their email? Okay, this will change the entire system. Okay, let's say if I update my email, so I'll have to update in all of the records with all of the connections also, right? If my primary key is stored inside, let's say, customer ID stored inside the product, order, all of the payment information also, so I will have to update it across the record. So that is not the good use of primary key. A good use is auto generated number in the backend itself. A databases usually do that you don't mess with it. It stays across the system. Okay, so you don't break the relationship between tables. Okay, so here what the basic entity looks like. We already know about this customer, orders, product. Okay, we have the customer ID and all of the attributes. Order ID, customer is the foreign key and the attributes, and same with the product. So these are the basics. Now let's understand the relationship and cardinality in ER diagram. This is very important. Okay, entity don't exist in isolation. There is no point of creating order table, payment table, product table separately. Okay, unless they have a relationship with each other. Customer places an order. Order contains a product. Product belongs to a category. These connections are a relationship, and the number of entities on each side of relationship is called as a cardinality. Okay, let's understand this. If you understand this, things will be very clear. Okay, there are three types of cardinality. You just need to know all of three. First is user and profile. Okay, we have one to one, one to n, okay, one to n, and many to n. Okay, let's understand this one by one. First is a one-to-one relationship. One instance of entity relates to exactly one instance of entity B and vice versa. What this means is that user and user profile, let's say there are two different entities available. So primary key here is the user ID, username, email, and user profile has a profile ID, user ID, bio, and avatar on other thing. A user has exactly one profile. A profile belongs to exactly one user. Okay, each user is associated with only and only one profile, and each user profile is associated with one and only one user. This is called as a one-to-one relationship, where the relationship is exist in one-to-one manner. The relationship exists in one-to-one manner only. A user can only have one single user profile, and user profile can only have one single user ID attached to it. It can't be multiple. Okay, so user exactly have one profile, a profile belongs to exactly one user. One-to-one relationship are relatively rare in practice. If two entities always have one-to-one relationship, you should ask, can we just combine this into the one single table only, right? This is a very rare case that you will have this, but again, it depends. If you want to split them, you can split them also, but if you want to keep this in one table because the relationship is one to one, you can define that. Now we have one to many relationship. One instance of entity A relates to many instances of entity B. This is the most common relationship in data modeling, and it is pretty simple to understand, right? Customer and order table, right? A customer can have multiple orders, right? Customer ID can have multiple orders, right? Each order is placed by exactly one customer. Okay, so the customer is one and the orders are n or multiple, right? So this is called as a one to many relationship, where one customer can place multiple orders. Okay, this is again how you define a relationship and the cardinality, right? When you design a data model, you have to define this cardinality also, like one user can have one single profile only, so that you can define the limitations across that, right? One, if it breaks that, let's say one user starts having multiple users profile, okay, that doesn't make sense, right? It will break the structure that we created. So you have to define the cardinality at the start itself. So one customer can have multiple orders. So one customer can place multiple orders. Each order belongs to exactly one customer. The many side holds the foreign key of the customer pointing back to the one of the side. For example, one customer can have many different orders, but one order, okay, one order can only have one customer. Okay, one order can only have one customer, but one customer can have multiple orders. Pretty simple English. Okay. Now this is the notation symbol that you can use to define. Okay, in when you are defining this uh, crow's foot notation, you can use this sign like single dash for one, a symbol like this for n, for example. So symbol like this, one mandatory, exactly one, so one to one. This is like O and line, one optional, it can be like 0 or 1. This is many mandatory, one or many, and many optional, 0 to many. Okay, this is you again used in academics. You might not to use this. You can directly use something like this, 1 and n, rather than using the symbol. In interview they won't tell you that you use the symbol. You can just use the numbers 1 to 1, 1 to n, and 1 to many if you want to do that. Okay, there is also many to many relationship, okay, or a junction table. So in many instances of entity A relates to many instances of entity B. A student can enroll in many courses. A course can have many students. Okay, so this is a many to many relationship. A student can enroll in multiple courses, and a course can have multiple students also, like in order, right? A customer can have multiple orders, but that particular order will have only one customer itself. For example, let me just give you this here. Okay, for example, we have order ID 1. We can use this, let's say, okay, let's just use this. Okay, this is order 1, this is order 2, okay, and this is order 3. Okay, and let's just update the customer ID for this one, 102. So here, this 101 customer that we have here, okay, 101 customer can have multiple orders. Okay, but this particular order, such as order ID 1, can have only one customer. This particular order ID 2, this is a unique order, okay, can have one customer. Order ID 3 have a one customer only. But this 101 customer, okay, 101 has two orders. It can have this order also. He ordered iPhone here, and he ordered, let's say, let's update the product ID here. Let's say he ordered MacBook also here. Okay, so product ID 3. So 101 can have multiple orders, but the order can only have single customer. So 1 to many. This is a relationship. But many to many relationship, we are using the example of student. Like student can enroll into the multiple courses, and multiple courses can have multiple student, right? A course can have multiple students. So here's the catch: you cannot represent many to many relationship directly with a relational database. Right? You can't do like many here and join it. You need a junction table. It is called as a bridge or associative table that sits between these two entities, that defines many to many or one to n relationship. It is like this. Okay, there's a student and there's a course. Then you will create an enrollment table in between that will join these together and represents a uh, relationship between each other, because there is no direct way. Let me explain this in a little bit detail so it will be much more easier. For example, how do we do this? Okay, uh, student student okay, and we have, let's say, what do we have? mm, we have student is my student ID. Okay, is my, let's say, student name, student name, and student is enrolled in a course. Okay, so I'll have course ID here. Okay, something like this. Let's say student 1 2 3 4 5, student name ABC, CDE, EFG, something AST, something like this. Okay, and course ID, let's say one student can have multiple course. So what we'll have to do in this case is that you usually have one row per student. uh, Again, this concept is around normalization. We haven't touched that normalization, so let me just write something like this. Okay, like let's say for now, just for understanding, there is a course table also, uh, course id, and let's say course name. Course id is, let's say, 1 2 3 and 4. It is, let's say, machine learning, AI, data science, and data engineering, like that. Okay, now this student can enroll, if it is a multi to multi relationship, a student can enroll into the multiple courses. So this student has enrolled into, let's say, 1 2 and 3. Okay, 3 courses. This student is 2 and 3, this is only 3, this is 4 and 2, and this is 1 and 4. Okay, something like this. So a student can have multiple courses. Okay, and course can also have multiple students. For example, here we define a student ID. Okay, to understand what are the students who are enrolled into this particular course. So for example, course 1, okay, has like 1 and 5. Okay, so this first student, okay, this first student and this fifth student is enrolled into inside the first course. Inside the second course we have 1 2 3, 1 2 and 4. Okay, so I'll just do 1 2 and 4, something like this. And then inside the third data science we have 1 2 3. Okay, 1 2 3. And inside this fourth one we have only a fourth number student. Okay, this is what we call many to many relationship, where a student can enroll into the multiple courses and course can have multiple students attached to it. Now this is fine, you can like write it like this, create a structure. We'll understand in the normalization why this is wrong right now. But the best way to define this multiple, you create a junction table. Okay, and let's say I will create a junction table where I'll just add I can add an enrollment ID, or I can directly do course ID. Okay, and student ID. Okay, and what I will do, I will just add the information about, let's say, first course. Okay, the course ID is 1 and the student ID is 1 also here, and course ID is 1 and student ID is 5. Okay, let me just add this separation here. Okay, then for the course ID second, okay, I will have 1, then copy paste, second, one, two, and 4, something like this. This is called as a junction table, where instead of storing these into this format where I defined everything at a inside a table and then use it, I will remove this from here. Okay, I will remove this from here, and then I have this junction information, which is the enrollment table I can have. Okay, so whenever I want to understand, okay, inside the course 1, okay, these are the students that are enrolled, so I can directly query it. Inside the course 2, these are the student ID that are enrolled, so I can connect this course ID to this table. I can connect this student ID with this table and get the information about the student and the course name also. So this is what we call as a junction table, where you add a table in between to define the many to many relationship. Okay, this is the core cardinality that we want to understand. One to one user can have only one user profile can only have one user. One to many, where a order can have a customer can have multiple orders, and one order can have one customer only. Okay, and many to many, where you can't directly join it, so you have to define a junction table. Okay, now let's talk about the step-by-step approach to define the ER. This is similar to the data model only. First, you define the entities, such as understand the business, and define the entities as a customer, product, category, order items. Define the attributes and keys. Same, you define the attributes and keys. Okay, then you draw the relationship between them, like customer orders, like 1 to 1. One customer can place 0 to many orders, so you define 1 to n. Order items, so order contains 1 to many order items. An order can contain 1 to many order items, so you define like 1 to n. Then product order item, one product appears into 0 or many order items, so each product item exactly refers to 1, so 1 to n. Category and product, so one category contains multiple products. So inside, let's say electronics is a category, right? Electronics can have iPhone or mobile phones, laptops, smartwatches. It's like 1 to n category. Okay, and then you build a complete ER diagram. So I hope you understood the core ER diagram. Again, these are the things, if you want, you can again read it. But this is the core of ER diagram that we want to understand. So we understand about the data modeling. We spent a lot of time understanding the ER diagram. Now let's talk about the normalization. Okay, let me have a water. You can also have a water. If you want, take a break and you can come back. But normalization is the core concept that we want to understand, because this is very important when we draw a data model. Once we understand this, then we'll quickly glimpse through some other topics, and then we'll likely start the hands-on practice. Okay, so normalization 1NF, 2NF, 3NF, and BCNF with a real life example. Now, normalization is one of those topics that sounds academic until you see what happens without it. Okay, what happens is that duplicated data, update anomalies, a customer changes their email and it's correct in one table but wrong in other 3 tables. A product gets reclassified and suddenly half of your report shows as the old category and half other show with the new one. Okay, so basically it looks something like this. Okay, we have the order table available, right? And inside the order table, order ID, customer name is Alice, and the customer email right now is alice@gmail.com. Then there is a second order, Alice orders, but the email has changed here. Then the third order, and the email is old one here. Okay, so here, first of all, this order ID and the customer name is a duplicate data. We are just storing the same data again and again. Okay, this Alice information is getting stored 3 times. So this is the duplicate data. And then there is an inconsistency of the data, because we are storing the customer name, customer email, and the order ID in the same table itself. When we update one information at one instance, this is getting updated. So we think that, okay, this is a different email and this is a different email. So we'll always get confused that, okay, why does this user have multiple emails available? Okay, so normalization exists to prevent this entire mess, right? The duplication happens, the inconsistency that happens in the database. We try to remove that with the normalization. Once you understand, you'll understand why we intentionally break these tables into multiple small table chunks, so that we have a proper table. Okay, so this is what it looks like, right? Let's say we have the order table created here that has order ID, order date, customer name, customer email, customer city, product name, product category, quantity, and price. Everything is added into one single table. Okay. In this, Alice has changed the email, so this is the inconsistency. City, as you can see, city is stored inside a different formats. The San Francisco is stored like this, SF is stored like this, San Francisco CA is stored like this. Is also, and update anomalies. And when you update something, when you delete something, all of these things happen, right? This is the single table and the informations are not stored properly. But when you normalize this table, right, normalize basically when you break this table into different chunks, okay, it becomes something like this. Okay, we have a customer table. We divide this entire order table into three tables: customer, orders, and order item. Okay, now customer will only have information about the one customer only. For example, inside from this table, customer information is the customer name, okay, customer email, and customer city only. Okay, right now we are storing this again and again and again, and causing the increasing the storage cost and computation cost. We will create a customer table that will have customer ID 1 and 2, customer name, customer email, and city. So we are not storing the Alice 3 times now. We are only storing Alice 1 time with one ID only. Okay, and whenever we want to use a customer information, we use the primary key of this table into other table. For example, inside the orders, we have the order ID and order date, and customer ID is used here. So we use, instead of using Alice Chen and email and the city and all of the other things, we just use the ID as customer one. So instead of storing three column and the data again and again, this large data, okay, we just store 111, the single numeric. So this reduces the cost and it's easier to maintain also. Okay, so if we change the email, okay, we just have to change one single cell only. If you want to update the email, we will have to update all of the email across the table, right? We will have to update all of the email. Okay, and same we divide the order items, like we use the order items ID as a primary key, then order ID here, okay, for that particular order, and the other information such as product name, product category, quantity, price over here. Okay, so customer data stored once. Each order refers to one customer ID, and each orders can have multiple items attached to it. So this is what we call as a normalized version. Normalization is a process of organizing your tables data, so each fact is stored exactly at one place. Okay, so one information is stored at exactly at one place, and whenever you need that information, you can get it from the referring a different table. It is a systematic approach to eliminating a redundancy and ensuring that when the table updates a piece of data, you update it once and it is correct everywhere. Right now, if I want to update the email, I will have to update it across all of the table that has the customer email to it. But if I have a customer table, I just have to go and update the customer table. That's it. Okay, this is called the power of normalization. The simple concept to understand is simple, right? If a customer email appears into the 500 order rows, okay, we have like customer email appearing in 500 order rows, and if you run a query and by mistake you just update it for 400 rows only and you miss the 100 rows, this will create an inconsistency across the table. You will see like different type of email for the same customer created, and on a small scale it is quite easy, but if you go in the larger and larger, like terabytes of data where you have like millions of customers, billions of customers, right, available in your data, at that time figuring all of this issue like into the large chunk becomes very difficult. You won't be able to even recognize that because you might just let it be and forget it, right? But if you have a consistent schema, normalized version, then it will be much more easier. That is a goal here. Okay, so normalization solves three specific problem: insertion anomalies, right? You can't add a new customer until they place an order because customer data is embedded with the order table. So if you want to register a customer, you also have to register. If a customer buys something, you also need information about the customer in the customer table. So a lot of times you might insert data into one table, but it is not available into the other table. So you might create an order into the order table, but the customer is not available in the customer table. So normalization actually solves this issue. Then you update the anomalies, the same example about the email. If you update some email, if you forget something, and then it will create the anomaly. And then the deletion anomalies. So this is basically if customer wants to delete the customer data, right? If you have a big table and if they want to delete a specific order, so that order will get deleted, but the customer information might stay into the database also. So if you have a proper a normalized form, you can manage this easily. Okay, So to achieve from this denormalized to normalization form, all right, we have three different main approaches. This is called as the first normal form, second normal form, and the third normal form. This is quite easy. Just pay attention. Once you understand this, things will become more easier. Okay, and we'll also understand when to use this normalization form. This is the final of sort of data modeling code. So once you understand this, all of the other things, we'll just take the overview and then we'll start with the hands-on practice. Okay, so first normal form. Okay, the rule, okay, each normal form has a rule. So the rule of first normal form is that every column holds a single atomic value, no repeating groups, no comma separated list, no array stuff into the single cell. For example, when I showed you this example here, right, let me just go this here. So in this is not the normalization form, because this student ID, okay, stores multiple course into a single cell. The first normal forms, the rule of first normal form says is that every student ID, okay, every student ID, okay, has a name and courses attached such as math and physics. Okay, every column holds a single atomic value, no repeating groups, no comma separated list, no array stuffed into a single cell. So this way, when you store, this is not right. Okay, as per the first 1NF rule, every cell must store a single or atomic value only, no list, no nested values, no structure. Okay, so we need to convert our table into this format where 101 student have a course, 101 Amit has this course, 102 Neha has this course. Okay, 1NF ensures every cell has one value only. So you, instead of storing data like this, you make sure you store the data like this. Okay, again, you can break this into a different course. Okay, that is a part of the second NF. Okay, but this is the first rule. Okay, you have to store data into the one single value only. This is a bare minimum. If your table does not meet 1NF, it is not really a relational table, it is a spreadsheet. Okay, so again, order ID, customer ID, product, and total, this product's information are stored like this. If you convert this into the first NF form, it is stored like this, where each and every product has one single row attached to it. Now, once you make sure your table is into the 1NF format, okay, meets NF, the rule of second NF is that meets first NF, okay, plus every non-key column depends on entire primary key, not just part of it. For example, okay, understand this. Okay, second and third NF are a little bit tricky, but it's quite easy. Every non-key column must depend on the whole primary key, not the part of it. What it means is that, let's say there is a student ID and there is a course ID, then there is a student name and the course name. So in this example, student name is dependent on the student ID, course name is dependent on the course ID. So if the rule says that every non-key means student name and the course name, okay, non-key column must be dependent on to the whole primary key, okay, whole primary key, not just part of it. So in this is a wrong example, because this is the entire part. The non-key column are part of the whole table, whole primary key, but instead we have to create something like this. Okay, this is called a second normal form. Every non-key column depends onto the whole primary key. That means student ID depends on the student ID, course name depends on the course ID only, and then we have a this junction table that joins it. So in this example, this student name has again student ID and course ID into a single table. Same, the course has this two as a single table. We divide this table into the small chunk, okay, and every non-key column only depends on the whole primary key, and it is not a part of it. Okay, it is dependent on the primary key, but it is not a part of it. So that is the second NF. Okay, first NF tells you that it should have a single atomic value. Now you divide it more and make it not a part of a whole table, but just depend onto the primary key rather than the being a part of the entire table. Here is the example of the same. Okay, we have order ID, product name, category, quantity, and unit price. Okay, now here order ID and product ID, okay, and all of this information are dependent on these two key. So the product name and the category depends only on the product ID, but the quantity and the unit price depends on to the order and product both. So what we will do in this case, okay, we will create the order items and the product information, where we will have the order ID and the foreign key of this product ID. Okay, we will use it here. We divide our table into the product information and the order information. This is what we call as the second normal form. So instead of these information stored inside a single table, and depending on the multiple keys, you try to create a multiple tables. In the simplest term, you try to divide your information into as many as table possible and have it a single primary key. Okay, now the third normal form, okay, third normal form says is no transitive dependency. So third normal form should meet the second NF, okay, and non-key column should not dependent on other non-key columns. All right, again, non-key column, that means product name, product category, student name, all of these are the non-key column, should not depend on other non-key column. It should only depend on key, nothing else. So in this table, like if the table is created like this, the department name is dependent on the department ID, and this department ID is dependent on the student ID. This makes department name dependent onto the student ID. It is not directly dependent on department ID here, okay, in single table. So what if you want to convert this into 3NF format? All we have to do is just create a department table. We store the department ID and department name separately, and we use the foreign key here. Again, the idea is still the same. You try to divide your tables into multiple small tables rather than storing it into the one single table only. The language or the definition of the 1NF, second NF and third NF is quite complicated. Like it uses the words like non-key column should not be dependent on the whole key. All of these are the complicated things used in academics, but the core idea is just dividing your tables into smaller and smaller chunks. Same goes here, right? The customer denormalized form, you have customer ID, name, zip code, city and state. So this, all you do here, okay, city and states are repeated for the same zip code. Over here, as you can see, the zip code is this and it is repeated same. If San Francisco zip code changes, you must update the multiple rows, risk of inconsistent data. So what you do here is that you create a customer table that stores the information about the customer ID and the name, and you just attach the customer zip code and create a zip code as a new table rather than storing it into the same table itself. So this is the third normal form. Now this is the edge case BCNF. We don't want to touch that because it will make things more and more complicated. If you want, you can read about it, but these are the three normal forms that you have to understand. One is the first normal form. Every row should have an atomic value. Second normal form, okay, the table should not be dependent onto the multiple key or should not be part of it. We should directly divide it. And third NF is basically it should not have a transitive property inside a table. Again, just divide the table. So you can read more about it, but I just want to quickly give you the understanding about the normalization and denormalization. The approach is simple. Just storing your data into OLTP system or transactional processing, you should normalize your data. If you are using OLAP system like BigQuery or what do you say, Snowflake, Redshift, you should use the denormalized data. Okay, so normalization usually used for the transactional processing like this: Postgres, MySQL, SQL Server. Writes are frequent, consistency matters, storage was expensive. This was the old way we used to do that. But denormalized form is used for analytical processing, used for reads are frequent, joins performance matter, storage is cheap. So the pattern is simple. For example, if I want to get the information about revenue by category by month, okay, if I use a normalization form, I will have to join these many table, okay, to get the information about the revenue by category by month. Okay, I will have to join these many tables to get. But if the tables are into denormalized form, I just have to join 3 tables and I will get the same value. The use case is different here. Okay, understand this, right? If I am storing my data into OLTP, I have to store data into the normalized form because I want to avoid all of this duplicate information and try to make the storage cheap and want to avoid the inconsistency across my application. But when I'm analyzing my data, okay, when I'm analyzing my data, I have to make sure I have a frequent few tables, such as I will convert my data model into a dimension model, a fact and dimension format where I can just have 2-3 tables, I can join it and get the value. So going from this OLTP to OLAP, okay, the change to this, okay, this is where we do our ETL, extract transform load. All right, this is very important to understand. Now where does the ETL actually fits? When you have OLTP system available here, okay, that is basically your website application API. For example, data vidya, I have my courses running, I have my all of these things are hosted. Okay, every data that I collect about the user are stored into the normalized form, so that the structure is maintained. But when I go from OLTP to OLAP, when I create a data pipeline to extract data from APIs, web analytics, apps, and all of the other things, and I merge this data, I create a OLAP based format, which is a dimension model. Here I will write dimension dimensional. Here I will write dimensional model. Okay, this is my data model. All right, today we are focusing on this. Tomorrow or in the next part we will focus on this. So when you do ETL, extract transform load, you extract data from data model or dimensional model into that has the data properly structured, and then you put it into the dimensional model. Okay, so you go from normalization to denormalization. Okay, and denormalization, if you want, you can read more about it. We'll tackle this into next part, but this is the core concept. Now let me just quickly skim through the foundation of this again so that we understand. So we have 5 approaches. We have like 3NF. This the normalization approach that we understood, 1NF, 2NF, and 3NF that we understood right now. Oh, what is happening? Wait, it's not loading. Yeah. So we have 5 approaches that we talked about. We have 3NF OLTP operational transaction. When we have the dimensional modeling Kimball that will look just will glance through it right now. Data vault, one big table and document or NoSQL. This we already understood, right? 1NF, 2NF, 3NF, BCNF, most production value. This you usually use for application like Uber app booking screen, e-commerce checkout. High write volume, lot of insert updates, consistency matter, single source of truth to the downstream. If your data model is not proper and not normalized, it will have a very messy data, duplicated values. It will be very hard for you to write the ETL pipeline and denormalize that data. Okay, this again you can take a look at this PPT again, the same summary of 1NF, 2NF, and 3NF. Okay, atomic values, every non-key depends on the whole key, so rather than this depends on this and this depends on this, you divide this into the second normal format. And same here, department is a transitive dependency on a student, so you create a department ID and store it like this. Okay, BCNF is again a more stricter version of 3NF. Basically, employee have a project. Okay, so you create a employee and a project ID separately. More granular version. Okay, then 3NF again, pros and cons. Pros are basically minimal duplication, strong consistency, easy to update, excellent for transaction. Cons are read queries requires many joins that we already look, slow for analytical aggregation, hard to scale for analytical workload, and schema is rigid, slow to evolve. Now this again, cons are here, but we don't actually run the analytics on top of the OLTP database. Second is a Kimball approach. Now this is the Kimball, again we'll go into the denormalization, fact tables, slowly changing dimension in the second video. If you want, you can again go through it right now after this video. If you want to learn further, I have it available over here. I also have videos available onto my courses, so if you want to go, you can go into the detail, understand about the dimension table, understand about scar schema, snowflake schema. I have actually talked about all of these in detail. Okay, if you want, you can always look here and move forward, but let me just go through the overview of it so that we can directly start building actual hands-on practice for Uber data model. So this is the vocabulary we need to understand. Fact table is a measurable event like rides, sales, the information that you can measure. Dimension table is a descriptive text, user table, driver, product information. There are 2 ways you can create a dimension table, the dimensional modeling. Star schema, one fact table at the center and dimension pointing to it. Snowflake schema, dimension normalized into the subdimension. And grain matters because this is the grain that you will be running your analytics on top of it. So this is a star schema example. This is a fact, right? That has a fact, amount, distance, duration, search multiplier, and dim user, dim table. All of these are the dimension table attached to it. There is also slowly changing dimension concept available. This basically says that again, dimensions like, user address don't change often. When you're creating a ETL pipeline, let's say it might be updated let's say email name, okay, email ID. It is updated alice at gmail.com. Now it is changed to alice.a.gmail.com. Now, when you create a ETL pipeline, how do you handle these changes onto the analytical side? Okay, there's a completely different framework for that. A slowly changing dimensions that changes very slowly. So there's a different ways to handle this. Like there's a type 0 that never change, type 1 that you directly do the override, you don't manage the history. Type 2 is basically you add a column such as effective from to effective from and effective to. Then there's a type 3 to also store the history. Type 4 create a separate table for history. Then dimension, again, pros and cons. Data vault is also basically the enterprise data warehouse with the audit and compliance. So again, there are some requirements if you are in the banking sector or healthcare sector, that your data should be properly handled and should be stored into a specific format. So you manage all of the information about that. There's a one big table. This is very modern. This is the new concept that is got popular because of the modern data warehouses. Uh, the basic idea of the one big table is that you store everything in single table only, because the storage is cheap and compute is cheap. Rather than storing the again information into the multiple tables, directly store it inside a single table. Write a single query inside one single table and you will get the output. So this is a concept of one big table. We'll maybe understand in the future videos, again available inside my course. If you're interested, you can check it out. OBT pros and cons. Okay, so we can understand this in future. So this is a one big table. And NoSQL database, again, a lot of times you might not want to go with the relational database because it is schema enforced. Relationships are quite tied to each other. You can't modify things quite easily. If you want to change the data type from, let's say, varchar to text, you will have to do a lot of changes for that. That is when the NoSQL or document database comes. It has a specific use case, for example, user profile, application conflict, or event logs. If you want to store, you can store it. It stores into the MongoDB, DynamoDB, or CouchDB. It uses the key value format, and relational database rigidity slow. Relational database usually slows you down because of the join. You have schema on read, horizontal scaling, a great fit for unstructured data, and fast for single key lookup operation. But again, modern data warehouses also handle the unstructured or semi-structured data, so you can use that also. But this is the usual framework or the approaches that we had till now, right? 3NF, Kimball, Data Vault, one big table, and document NoSQL. Again, the process that we already understood, right? Clarify the use case, identify the entities, choose the approach, define the grain, handle the changes over time, and then the physical modeling. Okay, so we understood the core of data model. Again, if you want, you can go deep dive into the dimension model once we do that. But what we will do now, we will go and do the actual hands-on practice. We will build a Uber data model, ride sharing application from the scratch onto our data vidya platform, so that you will understand the hands-on way on how to build the entire data model, the 3NF part, right? The 3NF application onto a data modeling case. Okay, so this was everything. Okay, so this was everything. If you want to take a break, take a break. And now we will start with our hands-on approach. Let's get started. So now we will build a hands-on data model. We will apply all of the principles that we have learned, and we will work on a ride sharing like Uber like application, and we will build the data model from the scratch. Okay, so all you have to do is just go to datavidya.com. Over here we were working in the learn section. Now we will go to the practice. Here we have a data modeling section available. Okay, we have data modeling questions from easy, medium to hard. The question that we'll be working on is on the medium level question. So all you have to do is just search right here. So we have the data model and also dimension model available. Right now we are going to work with the data model. Maybe in the next video we'll work with the dimension model. So just click over here. If you don't have account, you might have to create the account for this, and we'll get started. Okay, now for this we are going to again go step by step and build our entire data model. So as we understood while we were learning foundation, first we need to get started with the business domain, and then one by one we'll start building our data model. So let's just read the question. Okay, you are designing a database for ride sharing platform like Uber or Lyft. Create a schema to manage drivers, riders, rides, pricing, and rating. Okay, so we have to create a data schema to manage drivers, riders, different rides, pricing and rating. Okay, ride sharing platform must match driver with the riders, calculate dynamic pricing, track ride status in real time. Key operation includes such as how many available riders, how many available drivers are near the rider, what is the estimated pickup and cost, what is the estimated pickup time and cost, what is the driver's utilization rate, how do we implement surge pricing, can we detect and prevent fraud. Some of the requirements are track driver availability with the real-time location updates, supports ride matching based on the proximity, implement dynamic pricing, calculate fare based on the distance, time, surge pricing, manage ride status, life cycles and payment. Some of the constraints such as 10 million per driver, 100 million per riders, 1 million per concurrent rides, location updates every 5 to 10 seconds, matching latency less than 10 seconds, real-time search pricing, PCI compliance. Now these are the constraints usually applies in the real world, but we get the idea, right? We want to create a schema that starts with the managing driver, riders, pricing and ratings. Okay, so this is the question that it starts with. Now, the first thing is we want to build our the conceptual model. We can do that on Scala Draw itself. We will just draw rectangles here and we will actually build our logical model onto the platform. Here we'll just build the conceptual model. So here first we have riders, all right, and drivers. Okay, let me just copy this, paste this, and we have drivers, riders and driver available. Another thing we will need is rides. Okay, so rides. Okay, so rider, okay, will book a ride. So basically it might go something, this is very rough. Okay, we're just thinking out loud like what it might look like. So rider will book ride. Okay, driver will basically sort of drive, take the ride. Okay, and maybe drive. This is the initial. So we have a rider that will ride, okay, and driver that will take that ride and go from different location. We can also add vehicle if you want. Okay, so vehicles. Now driver will drive this vehicle. Okay, will drive this vehicle. What else can we add? Right, we added riders, basically our user, right? Different rides that the rider takes, drivers that will drive, that has the vehicle also. We can also have something like payments. Okay, payments for now. It's just rough idea. Again, rider will make payments. Make payment. Okay, make payment for this particular ride. Okay, make payment for ride. Okay, and I think based on the rights, the driver will get that. Payments is done. Payments and location also matters, right? Driver has location, so we can also store driver location, and this will store the driver location, something like this. So this is very rough idea. Then we can also have ratings, uh, because when we use Uber like application, right, we want to make sure we rate people, so rating is also available. So again, rider can rate. Okay, rider can rate, uh this is driver rating. Okay, can rate, let me just update this, can rate to a particular driver. We have payments, ratings done, rides done. We also have, like, let's say search pricing. We can add it right now here. Search pricing. It required like our to add. See how many available near drivers. We can just add based on driver location, estimated pickup time and cost. We will just add it onto the uh, attribute, driver utilization rate, search pricing. Okay, we can also add something for search pricing. We added that. And can we detect and prevent fraud? Search pricing, driver location is done. We can also add dynamic pricing for based on pricing zone. So if it is raining or something, we can add that. I think we can connect this afterwards, but this is a good place to start, right? Oh, all I did is just was thinking out loud that if I were to design or Uber like application, okay, what are the different entities, right? These are the different entities that I can think about. Now, once I define the entities and the rough idea, then I can start actually building the attributes that are attached to it and the relationship with that. Okay, so once this is done, we can just start going one by one and start adding the attributes. So first we'll start with the basic one. So all you have to do is to come to our data model canvas. Okay, this is where you will have all of your tables that you create, and this is how you can create add a new table. So add a new table, you can just write Control P, and we will do riders. Okay, this will be our first table. Let me just minimize this. Okay, now inside the riders, first will be our rider ID. So I can click this and just say rider ID. This is my primary key. Okay, this is unique and this is integer. I will do save. After the rider ID, I will do email. Okay, because as a user, right, if I'm going on a platform, uh, I need email. So this is my email, varchar. Okay, after email, I will say phone number. Phone number will be again varchar. After that, we have the name of that particular user. It can be nullable. Then what else do we have? We have, let's say, profile image URL, because when we create a profile, we also need to store the user profile information. Let me just zoom this out a little bit. Yeah. What else? What else? What else? Is this profile active or not? Okay, we can also add that. So we can add a boolean here. So if this profile active or not. The profile created at, okay, created at, we'll add as timestamp. What else? We can add an age also of rider. I think that is a good age. Age in, let's say, we can keep it varchar. This is fine. Let's put the age over here. What else? What else does the rider have, right? If I am registering on Uber, right? You, let's say I'll add my phone number, I'll add email, I'll go next. I'll create my profile, I'll add my name. I can add my location also. I think that based on the ride also, so it is latitude, longitude. So let's just go with this. Okay, right now our rider is sort of created. Okay, after that, rider will ride on different rides. Okay, so I will create new table as rides and I will add it. Okay, so for rides, again, first of all, I can edit this and I can add ride ID. Okay, this integer, primary key, unique. Now ride is going to be taken by different riders. Okay, so we will need a rider ID here also. So I'll just add rider ID. Okay, this is not nullable, and yeah, I'll add as integer and I'll add this field. I can connect this rider ID to this ride ID here. Okay, and the relationship is that, mm, okay, let's not add relationship right now. Let's just first work on the adding a different attributes. Okay, after this we will also, when we create a driver table, we will also add a driver ID here. Okay, so let's just add that for now. So I will add driver ID, that is integer, and also not nullable, and also vehicle ID, vehicle ID, and again this is integer, not nullable. Okay, so these three things I've added. For this I will also have to create a driver table and vehicle table right now, but other than that I will add other information that are required for different rides. Now when we are designing Uber like application, okay, for different rides that are taking place, we need a pickup location, okay, that is a latitude, longitude, and the drop location, that is again for the latitude, longitude, and the address also. Okay, so it will look something like this, which is pickup latitude. Okay, latitude, longitude, I think I don't know if you know about this, latitude and longitude. Okay, usually when you on Google Maps, if you need a basically on Earth, this is a latitude and longitude, and there's a numbers attached to it. So based on that number, you can find the exact location for that particular area. Okay, so this is a pickup latitude. This will be into the decimal format. So we'll keep this decimal. Then pickup longitude. Same goes with the decimal format, and I'll add this. After that, pickup underscore address. Varchar, this is fine. Other than this, what do we have, right? This is done. Again, same goes for the uh, destination latitude, same decimal, add fill, destination longitude. Okay, and what else? What else? Destination address. That is varchar. Okay, this is done. Um, okay, we have added pickup, we have added destination. Now we can add more and more things if we want, such as let me think what the ride does have, right? Requested vehicle type, requested something like request requested something like requested vehicle vehicle type. uh, Again, we can add this on vehicle table also, but okay, for the rides also we can keep it here for now, because a user can specifically request a different vehicle type. Okay, so we can add a vehicle ID also, but let's just add vehicle type here itself. Status of the ride, if the ride is ongoing, completed, something like that, we'll add estimated fare. Okay, uh, we'll add this as decimal, and then ride duration is also there. Duration, estimated fare. Okay, estimated fare, then final fare. We that usually show it on the application, so final fare. After this, okay, let me just yeah, make this small. I hope you guys can see this. Final fare, then distance. Ride also has distance in kilometer, so I'll add distance. Duration of ride, I don't think we added duration. Duration in minutes. We'll keep this integer, and we'll add a time also. So requested at that particular timestamp. Match. So we request at one place, then we match. So matched at that particular timestamp, and we also have pickup completed time and cancelled. Okay, so we can also do that. So pickup time, uh, pick pickup at, then completed at, then cancelled at timestamp, right? If you want, we'll normalize it afterwards, but this is something to get started with. Okay, so we added a lot of different columns here. Let me make this big. Okay, so this is our rights, and rights have a lot of things. Okay, so over here what we did is we added the ride ID, then we have the rider, driver ID, vehicle ID, pickup latitude, pickup longitude, the location. There's a typo I've made. Pickup address. Let me just update this. address, okay, pickup address, destination latitude, destination longitude, destination address, requested vehicle type, might not need it, but let's just keep it for now. Then status of the ride, that is, it is ongoing, completed, cancelled, whatever it is. Estimated fare, final fare, uh, that we want to track. Distance, kilometer, duration, okay. Requested, add, matched, pickup, completed, cancelled. So all of the different events we want to store the timestamp. So rides are done. Rider is here. Okay. What is missing is driver one. Okay. So let's work on the driver. Now driver is again as a driver. Come. This is drivers and the driver. Okay. A driver will have again same. First of all, driver ID. So driver underscore ID same. After that we have email. Okay. Email skip. After that we have phone number again where care, um driver's license, also driver has license. So also before license we have driver name, then license number. It can be alphanumeric, so it can be some words or number. Same profile image URL of the driver. Rating, okay. We will connect, we can connect with the rating table also, but for now we'll just add rating as it is. After that we'll update that, so I'll add the rating here only. Total rides by the driver, this is integer. um is driver currently active? We can add the boolean here for this. Is driver currently online? Okay. Is he taking rides? And the created at, we have to usually add to track the profile creation of the person. So this is timestamp. Good, looks good for now. If needed, we'll add more and more things over here. Okay. So driver is done. What else, right? So we initially did the rider, driver, riders. Okay, these three things. Vehicles. So we can also do vehicle now. Uh, to at least have 4 tables available. So these threes are available. I'll also add vehicles. Okay. Okay. I'll add vehicles, and for vehicle, same. Let's just go with that. First is edit. So vehicle will be connected to the driver. So we'll have, because driver is going to drive that vehicle. So first is vehicle ID. Okay. Then second is driver ID, because that particular driver is going to uh, attach to the vehicle will have driver ID attached. We can also do vice versa, but right now we'll keep this here only. And what do we have? License plate. Okay, what is the car or the vehicle's license plate number? uh, Company, made company, so we can have make something, okay, which is a, okay, company, vehicle company. Okay, so company. Okay. Model, year of that car, color, vehicle type, mm, number of seats available in the car. Okay, integer. uh, is active also, if this vehicle is active or not. And what I think, what else does a car have? Like weight, I think we don't care about that. uh does have AC. Okay. But AC usually cars have it. We can add it if we want. What do we have? Okay. You also think while you're doing this. So I have like vehicle ID, driver license, company name, model name, year, color, vehicle type, seat. When you order an Uber, right, what do you usually see? So type, model is the same, like if it is XUV, SUV. You can also add that company is added, model is added, color is added, year is added. I think, yeah, that's fine for now. Okay, I think looks good for now. What we'll do, we'll just make a connection for now, the cardinalities that we want to create, and we'll go from that. So ride is our main table, okay, and everything around will keep. So we can start. So we can start making a connection. First of all, we have is with the rider. Okay, rider is our user. So let's just make the connection here. So the okay, we'll connect with the rider ID. Uh, the cardinality, like 1 to n, is it 1 to n? It is 1 to many to many, or it is 1 to 1. Okay, so one rider, okay, the rider or user can have one ride or multiple ride. Yes, one rider can have multiple ride, that is possible. I can book multiple rides, okay, throughout the time span. uh One rider can it one ride, can it have multiple riders? It is also possible if it is a pool, right? Uber pool where you can have multiple riders into the one single ride. It is possible. So this is more of a many to many, okay, than one to many. So I think this is fine for this. It can be also 1 to n, like one rider can have multiple rides, but one ride can only have one rider if it is like a single rider booked from a single app. But we'll go with by thinking that we it is also Uber pool, so it is supported. Okay, so I will connect driver ID here. Okay, there is some bug. We'll get it fixed. But basically, I'm connecting driver. Okay, driver ID with the driver ID of this. Okay, and the cardinality is that uh one ride can have one driver only. Okay, one driver can have multiple rides, but one ride. So the cardinality of this is that one driver can have multiple rides. So it is sort of like in reverse. Let me change it this way. Okay, we'll create a relationship from here. So driver to the driver ID here. Okay, so one driver can have multiple rides, and multiple rides uh, can't have multiple drivers because driver is always one. So this will be 1 to n with the driver. Then we have the vehicle. So we can connect vehicle with the vehicle ID over here, and the cardinality is same, like one vehicle can have multiple rides, but multiple ride can't have multiple vehicles. Maybe it is, but I think, yeah, this is the simplest form. If you click to this auto layout, this will basically do the auto layouting of this and like put everything in place. So this is the simplest one version we have made till now. All you can do is just click onto the submit for now, and this will read your entire data model and send it inside the backend, the AI evaluator. It will evaluate the entire data model and it will give you the result of how your current data model is actually looking. And based on that, we can improve it. Again, the part about data model is that it cannot be 100%. Okay, you cannot get like if the data model is done, it is completely fixed. Okay, it is evolving process. Like once you create something, then you find out, okay, we need to also add this part, we also need to track this data, we also need to work on this. So you start adding and you start adjusting your data as you move forward. But initially you just start with the clean plate, that okay, I want to start with this. Okay, we will build this is my assumption that okay, these are the different things we need to track. Once you build this, after that you start taking more and more ideas. Okay, we also need to add ratings, we also need to add search pricing, we also need to have dynamic pricing based on the weather, we also want to track that. So as you move forward, you can add it. So the score of our data model came and it is around 6.2. Okay, this is a complex domain. Ride sharing involves real-time production tracking, dynamic pricing, payments, bi-directional ratings. At this level, I expect you to see the most of the subsystem represented, even if it is simplified. Okay, so completeness is our 5. Okay, you got foundation entities like riders, drivers, vehicle rides. They are connected sensibly, but several code parts of the problems are missing. Driver location table for real-time tracking, no table payment, no payments table for money flow. Okay, let me just zoom this a bit. Then no ratings for table bi-directional search pricing zone is not available. Relationship accuracy, I think it makes sense. Normalization mostly clean. I think we might have to one concern, rating and total rides or driver are denormalized aggregate. We'll take a look. Integrity constraint, I think every table has primary key, good. There are gaps like email and phone are both drivers should be unique. We'll add this afterwards. Practical alignment is 5. Okay, so I think there are a few issues we still have to figure it out, but let's just move forward. So I have minimized that right now. Wait, let me just reset this. Okay, AI feedback is available over here. I've kept it here. So what we will do, we will add more and more tables for now. Okay, first build a base structure and then go for the improvement from there. Right now, we'll just keep this as it is. So we'll add all of our tables that we had, like driver location, payments, ratings, and all of the other things, and we'll take it from there. Okay. So we have vehicles available, we have drivers available, we have riders available, we have ride available. Let's add a driver location table for now. We'll add a new table here. Let me just minimize this also, so we have more view. Driver underscore locations. Okay. I'll create this table. And for this table, let me add first this edit as location underscore id, that is integer. Then I have driver id. Okay, nullable unique integer. I think this is a foreign key. I don't need unique constraint here. It's fine. But this is a foreign key. This will automatically get added. Uh, yeah. Other than that, we have latitude. This is a decimal. Longitude. Again, this can't be null. We'll update the above also. This edit. Keep it nullable. And then heading. We'll keep integer. Heading to particular location. Then we have speed, kilometer per hour. You can also use any other metric. We'll keep decimal, not nullable. Accuracy meter. Meters, we'll keep this as int. Updated at the last location. Timestamp, not nullable. Okay, so this is my driver location. I can add it as it is for now. Other than that, what do I need? I need pricing zone. So I'll add a table at uh, pricing zones. Okay. This pricing zone, basically based on a different zone, we will keep the pricing. So first of all, we have zone ID, and after that zone name, varchar. Mm, Again, we want to define our zone into a polygon, like we'll do a boundary around the map. So we can also add around boundary polygon. Boundary, okay, we can add something like boundary underscore polygon. Okay, this is integer. Yeah, this is fine. After that, base rate per kilometer, we'll add a rate into decimal. Um, Base rate per minute. Okay, same, decimal, not nullable. Minimum fare for that particular zone. Minimum fare, which is our decimal, and is active. Okay, is active. Are we available on that particular zone or not? Okay. This is fine. I think pricing zones we have added. After that, let's just add search pricing. Search pricing. In the search pricing, what do we have, right? We have search ID. Okay. After that, we have zone ID. So we will define our pricing zone search. We'll connect this together. Let's just keep this integer. Um, Multiplier. If we want to search our price, we have to add a multiplier that there also. So multiplier We'll keep this decimal. So we want to 2x price, 3x price. We can add that. What do we have? Like start time of the search, start time, timestamp, and end time, and timestamp. I think this is fine for search pricing. After that, we have rights. We need to add a payment information. Let me just put this. This will get more and more complex now. Now we'll add payments when users make. Okay, payments will might have a first payment ID as usual. So I'll add payment ID. After this, I will have ride ID, integer uh, amount. Okay, we'll store the amount of the payment that is being made to that particular ride. This is decimal. Amount can't be null. Payment method also. Payment method, is it card? Is it UPI? Whatever, right? Varchar not nullable. Status of the payment, is it captured, cancelled, refunded? We can add that. Mm, Payment gateway transaction ID also we need to add. So we'll do like gateway transaction ID. Okay, this will be unique. We'll keep this integer. We can keep this varchar also. Sometimes it is alphanumeric. Then failure, if there is a failure reason, so we can keep this varchar. It can be null. Processed at, we add a timestamp for that. Let's just keep it null, and created at same timestamp and not null. Okay, the payment is done. Are we missing anything? I think rating is missing. I think rating is missing. Driver location, search, price, rising zone, driver, vehicle, rides, payments, riders done. Let's just add rating last, and we'll start connecting, and then we'll see if we want to add more. Okay, so we'll add rating. Let me just add ratings. Um, Rating ID. Okay, rider ID, integer. We are giving rating to a rider, so rider ID. Then rater type. Okay, let's just keep the rater type. Uh, Rater ID. Okay, so here, like the way it happens is that a rating is done both way, right? One person like driver can give rating to user or the rider, or and rider can also give rating to a driver. Okay, so we want to add both of the things. So for example, rater type, it can be a driver or a rider. Okay, and we add a rater ID based on the table, based on the type. Okay, integer. And then we also have a ratee type. Okay, that person we are rating to, and also ratee ID as integer. Then number of stars. Okay, we'll keep this integer. Stars. Comment, if we have anything, this can be null. And created at as timestamp. I think this is fine. Okay, for now, we can like start joining this and see how it looks. So for example, let's take payments first here. Okay, let's just, I think this is getting complex, so let me minimize this for now. Okay, we have more view available. Rider will keep it over here, driver will keep it over here. This, we have payment, right? So payment and the rider ID. So with the payments, we'll make connection of the rider ID with the rides. What is happening? Rider ID with the rides. Okay, and the cardinality for that will be 1 to n. Okay, because a rider can make multiple payments attempt. It can be with the card, UPI, sometimes fails. So this is fine. So payment is okay. Let me update payment 1 to n, save. Okay, so payment is done. We also have driver and the vehicle. Okay, so over here we also have to connect driver ID with the driver ID of this. Okay, and the cardinality of this will be again 1 to n. A driver can own multiple vehicles. Okay, each vehicle can belong, and each vehicle can belong to exactly one driver, so that is fine. Then driver to driver location. So over here we can have a driver ID connected with the driver ID of this. This will be again 1 to n, because each every active driver pings GPS every 5 to 10 seconds, or uh, like every driver GPS. Okay, this will be again 1 to n. Every driver pings the GPS location 5 to 10 seconds, so there will be multiple rows, thousands of rows created for it. So this is again 1 to n. Then we have, again, this is getting complex. We will again do the auto layout. Search pricing and pricing zone are different here. So pricing zone to search pricing, I will connect the zone ID to this, and this will be again, a zone can have many different search pricing event. So it is 1 to n. Rider and rides. Okay, this is done. Then what do we have? With, we have a rider with rides, or then driver with rides is there. A vehicle with rides. Rides and payments are connected. We have ratings. Okay, so rides and rating, which we have rider ID and the rating available over here. This is again 1 to n. It can be many to many also. After a rider, okay, after a ride, usually both rider and driver rate each other. So it is like two rating rows. Each rating row belongs to one. So this is like we can have a double arrow created, but the best way is like either we can also add a rater and ratey ID joined, but that won't make sense. We can just directly join the rider ID to this, and I think that's about it. I think we pretty much joined all the tables. Let me just auto layout this created this layout again. Uh we have the functionality to hide this labels, but for now we'll just keep this as it is, and we'll submit to AI one more time and see what the results are. Usually if we get any point above 8, 8.5, we are in a good place, because that is a green zone. If it is below 8, we'll try to see what are the different things we need to fix. Again, data modeling is something that you keep working on. It is not something that okay, you do it once and it is done. You have to keep iterating it. You have to keep figuring out what are the issues. So let's just wait for the AI review, and it will take some time because the data model is quite long. It will analyze the entire thing, all of the query, and then it will give you the final result. So let's just wait for this, and then we'll move forward. Okay, so the database schema assessment came and we got our point around 7.4. So for medium level rights schema, you should cover all the estimated with the correct relationship, a reasonable and a complete well designed schema on 9.9 plus. You are meeting most of the expectation for medium comprehensive entity coverage throughout the structure. The foreign key wiring bug and missing rider to ride link are the main thing that's keeping this from 9. Okay, so there is some issue. So completeness, we have 8 to 10. Okay, you have captured most of the key entities: rider, driver, vehicle, rider, drive location, pricing zone, search pricing, payment, rating. All are here, which is great. The big miss is that rides has no foreign key to rider. Okay, riders are directly defined but never linked. So which is rides has no foreign key to riders. Let me check that. Okay, rides has no foreign key to rider. This one rider, okay, it is attached to rider ID. Rider rides, okay, it's not rider, it is rides, has no foreign key to uh rides has no foreign key to riders. Okay, let me update this. Let me delete this. Let's just add from here. Okay, rider to this. Okay. Mm-hmm. Never link the request. Also, there is no link between rights and pricing zone search pricing, so you can't trace which search multiplier were applied to the given right. Yeah, this is the one that we missed. Let me just put this inside. Okay, search pricing. This pricing zone, search pricing. So inside the rights, we can add a zone ID also. So open the rights and add zone ID integer. Okay, and you can drag this on the top over below this. Where did it go? Yeah, up over here. Okay. Let me just collapse this, and zone ID I can connect with the zone here. I'll just put this here. I'll just put this here, and I'll connect zone ID with this to this. Okay. After that, relationship accuracy, I think we made some mistake. Vehicle driver correct, driver location to driver correct, search pricing all look good. However, two bug, payments dot ride ID references rides dot rider ID. Okay, so ride ID should reference to ride ID from the payments. Where's payments? Okay, payments. Okay, so this is a ride. Okay, yeah, exactly. So let me remove this. Okay, and instead of rider, I will connect ride to this one. Okay, let me just submit this again and see how much code do we get. Okay, let's just wait for this and we'll continue from there. Okay, so I think this is fine. Relationship accuracy we need to fix is that there is a real issue in ratings. You have a rider ID as a foreign key to rides, but column should be probably linked to ride ID, so that which ride is rating. So I think so also. Hmm. So there is a real issue in ratings. So you have a rider ID as a as in foreign key to rides. Okay, rating rider ID to the rides, but the column should probably link to the ride ID. I think the same. I've linked rating to the rider instead of ride ID. Where is that rating? Okay, again, let me remove this and connect this. Yeah, this we added this as a rider, but I think we this is around the ride. I think the typo is made ride ID, and we connect this ride ID to this one. Okay, just like this, I think we might have made a mistake. Let's just look at this. Ratings is fine, right? The payment is fine. This is also fine now. Driver to this driver ID is fine. Vehicle to driver ID, vehicle ID, rider to this is fine. Okay, AI feedback. Let's check. Column. This is fine. This is fixed. uh rider has no rides has also rides dot rider ID has no foreign key to rider at all. Rider, we have added this. Let me add from this to this. Okay, AI feedback, I think this is fine. Normalization is fine. Integrity constraint, okay, every table has primary key. Rider dot email and phone number should be unique. Okay, rider, inside the rider we have email and the phone number that should be unique, so we can update that. Again, the use of AI is basically helping you to understand how you actually structure this, right? So email, we give this unique, and phone also we give this unique. Then and same for driver, email for driver, phone number and license especially should be unique. So for driver, email should be unique. Uh, Phone number should be unique. Name should be unique also. And oh, not the name. Wait, yeah, I made a mistake. The license number should be unique. After this, little unique by vehicle license plate should be unique also. Also, Silicon, there should not be not like okay, that is fine. For now, license plate should also be unique. Vehicles dot license plate. Okay, let's fix that also. We'll go vehicle license plate, edit, make it unique. Okay. Let's just submit again one more time and see where do we stand. So we had 7.5. We fixed two relationship issue and some unique and null constraint. If this gives around 8 to 8.5, I just want to get above 8 and 8.5. If we get that, then we are good to go. Then you can spend time and try to reach it by 9. I'll give you the challenge at the end. But if we reach 8 to 8.5, then we are in a good zone. So the assessment came, okay, most of the issues were around the relationship and the typos that I made. So completeness 9, relationship accuracy 9, normalization 9, integrity consent, practical alignment 9, 8. So most of the things are in a good place. Again, you can add more things if you want to reach above the 9 score. It is doable. All you have to do is just read this, see what are the issues that we have. Right now the rider life cycle timestamp shows you the state. One gap, there is no payment methods table storing the riders cards in wallet. Right now you can enter that. This will increase to 9.25 or something. Relationship accuracy also, you can check this. Normalization also, if you want to do more, you can also do this. Like total rides and rating also, you can denormalize that. Like this also, you can there is more recommendation also, uh, to update like pricing zone from integer to JSON to text. Again, data modeling is something that is an iterative process. You keep improving as we move forward. There is no 100% here. Again, if I were to spend time making this 100%, it will take more 2 to 3 hours. That is a assignment to you guys, that if you want to improve your data modeling skill with AI, you can use this. Okay, try to make it more uh, production ready. Right now we are getting this much, but if you spend time on this, if you improve the relationship of this, you can make it a full you can make it a production level data model for this. Okay, so this was everything for this. Like we have covered a lot of things from the start. This was from basics, different layers of data modeling, OLAP versus OLTP, ER diagram, normalization, different normal forms, understood the top level of the denormalization, fact dimension table, and all of the other things, and build a right sharing Uber type application for the data model. Okay, now the assignment for you is that improve this data model. If you want to practice more data model, the easier one, okay, I highly suggest you to go to datawizard.com. You can find for free lot of different data models are available to you. You can practice the library management and build a library like data model for that. Like this you can do for most of the data model. These are the questions that you will be asked in the real interview, so you can spend time practicing that. If you want to master data engineering, if you want to upskill in data engineering career, then we have the everything step by step available at one place. So from you will get all of the learning guides that are in detail with videos. We have around like 500 plus learning guides, 200 plus videos available that will give you a core understanding of foundation, SQL, Python, data model, DD system design, cloud infrastructure, Airflow, Kafka stream, behavior. This will help you to upskill. We have 20 plus projects available also here, like that can help you to build a real projects and add it in your portfolio. We also have a practice playground, like a lead code for data engineers, where you can come here, practice PySpark, Python, SQL, write code here, again get evaluated by AI and improve your skill set. We also have data modeling section that we saw. We also have architecture design. We'll also build architecture in future and review it. Resume review, some of the more resources are available. So if you are interested in upscaling data uh, engineering and build your skill set, pass the interview, this is the place. Data Vidya is the place that you come to. I hope this video was valuable for you. You learned something new. Do let me know in the comments if you like something. Okay, do let me know in the comments your thoughts. If you have any recommendation, do let me know. And so this was everything for this video. Do let me know if you have any recommendation, and I will see you in the next.